Hello, my name is Jeff Gullett, and this is a presentation on the theory and implementation of the Miller-Rabin Primality test. This kind of covers what we're going to go over, but let's just jump right in. So first off, why should we care about large primes? Well, transport layer security, the replacement for SSL, is the cryptographic protocol that enables secure communication over the internet. So anytime you enter a credit card online to make a purchase, or you're viewing your information in MyCU info, public key cryptography is an integral part of that to make sure that other people cannot eavesdrop on your session. So TLS requires a number of cryptographic protocols in order to function. The most common that uses large prime numbers is called RSA, which stands for Revest, Shamir, and Adelman. And that is the same Ron Revest who wrote our textbook. There is another class called elliptic curve cryptography, and some of those curves rely on prime numbers, but RSA to a much larger extent uses primes, and that's where we will focus in this presentation. Of the top 8 most popular websites in the US, half of them use elliptic curve cryptography and the other half uses RSA. And you can see I threw MyCU info on there for RSA as well, just because everybody in the class is familiar with it. Both ECC and RSA are in the BQP complexity class, which means that if a quantum computer is available, Shor's algorithm would break both of these algorithms. Break meaning that they could be solved in polynomial time. Right now, there is nothing that is quantum resistant as far as public key cryptography goes that is used in practice, so that is something to keep an eye on as we move forward. So the Miller-Rabin Primality test is an efficient, randomized, probabilistic test to determine whether an odd number is prime. It's based on Fermat's little theorem, and it always states that a prime number is prime, but occasionally it will say that a composite number is prime, but the probability of that happening is less than 25%, and as we'll see later, it's typically much less. There are a lot of other general primality tests, but Miller-Rabin was due to the work of Gary Miller and Michael Rabin. And the work of Miller, he proposed a deterministic primality test, but it's based on the still unproven extended Riemann hypothesis. A few years later, Michael Rabin converted that to a randomized primality test that isn't dependent upon any unproven hypotheses. And that is what we know today as the Miller-Rabin test. These other 3 tests, APR, ECPP, and AKS, were all somewhat important. APR being the first that was much faster. It was sub-exponential than other known deterministic algorithms at the time. ECPP is important because it has a very good heuristic runtime, and it generates a certificate proving primality, but the worst case runtime has not been proven to be bounded. And the final test there that I will explicitly list is the AKS primality test, which is the first deterministic polynomial time general primality testing algorithm. While it is important in number theory to prove that the primality testing problem is in P, the actual observed performance of that test is very poor. So typically we will use other randomized tests in its stead. There are a number of other primality tests, some of which are general and others which are specific to certain types of prime numbers. But the focus of this presentation is the Miller-Rabin primality test, which is used very frequently in practice. So Miller-Rabin has a couple of advantages over other primality tests. One of the most predominant is the false positive bound is proven to be no more than 25%. A lot of the other randomized tests only have a proven bound of 50%, and in fact, Miller-Rabin is oftentimes very much better than 25%. So you can do very few rounds of Miller-Rabin to get the same quality that you could get with many more rounds of these other tests. The runtime is bounded by log cubed of n. If you use fast Fourier transform-based multiplication, you get that down to soft O of log squared of n, where soft O basically ignores the factors that are much smaller than log squared of n. And the final advantage is ease of implementation. The most complex operation in Miller-Rabin is modular exponentiation, which is fairly straightforward to implement. So the Miller-Rabin test is based on Fermat's little theorem, which states that if p is prime, then all integers a in the range 0 to p satisfy the equation a to the p is congruent to a mod p. So the proof of Fermat's little theorem only requires two facts. One, that the modulus operation is distributive over both addition and multiplication. And secondly, the binomial theorem that states that x plus y raised to the power m is the sum from k equals 0 to m of the binomial coefficient m choose k times x to the k times y to the m minus k. There are a lot of proofs online for Fermat's little theorem, but the binomial one is the one that I found to be the simplest. If you're interested in it, Wikipedia has a great page explaining a number of proofs of this theorem. But let's dive into the one that uses the binomial theorem. So we're going to prove this by induction. The base case that 0 to the p equals 0 mod p is trivially true. The next step is assuming that a to the p is congruent to a mod p, then a plus 1 to the p is congruent to a plus 1 mod p when p is prime. So given the binomial theorem, we know that a plus 1 raised to the power p is the sum. And if we expand that out two steps, so we expand it to the binomial coefficients here, and then we expand each of those binomial coefficients out. So p choose 0 is p factorial over p factorial, plus p choose 1. And you can see I've expanded each one of these out on the bottom here. Other than p choose 0 and p choose p just become 1. The important thing to note here is that every single one of these terms has p in the numerator and it does not have p in the denominator. Since we know that p is prime, then we know that nothing in the denominator here divides p, and therefore every single one of these terms in the middle is divisible by p. Because we can distribute the modulo operation over addition, every single one of these terms in the middle becomes 0. So this is 0, this is 0, this is 0, and this simply becomes a to the p plus 1 mod p. Finally, we notice that the inductive assumption was that a to the p is a mod p, and therefore this entire equation simply becomes a plus 1 mod p, which is exactly what we wanted to prove, that a plus 1 raised to the power p is congruent to a plus 1 mod p, and therefore Fermat's little theorem always holds when p is prime. So it turns out that the contrapositive of Fermat's little theorem is also true, typically. That if n is not prime, then a to the n is typically not congruent to a mod n. And that's true for at least 75% of the possible values of a. Keith Conrad's notes listed in my bibliography has a great proof of this fact, but we're just going to take it as fact and move on. So if a to the n is not congruent to a mod n, then n is composite with 100% certainty, and the base a is called a witness for the compositeness of n. Otherwise, the base a is called a strong liar. Strong liars indicate that n is a strong probable prime to base a. Again, regardless of whether or not n is prime, we call a strong liar if it says that n is prime. That is just a notation used in this algorithm. Note that the bases -1, 0, and 1 always satisfy Fermat's little theorem when n is odd, regardless of whether n is prime or composite. Therefore, a will be chosen at random in the Miller-Rabin test from the range 2 to n minus 1. Finally, I'll mention that people have found through exhaustive search sets of bases for Miller-Rabin test that are sufficient to deterministically state that any number within a certain range is prime. So for 32-bit numbers, it is sufficient to test 2, 7, and 61. And that will deterministically tell you if all three of those tests say that a to the n is congruent to a mod n for each of 2, 7, and 61, then a 32-bit number is with 100% certainty prime. These numbers exist for 64-bit numbers as well and other limits. And you can find things up to groups of these numbers up to 7 listed on this website that I have at the bottom of this slide. So I have created this tool that is a web page where it graphically shows you what happens as you exponentiate a to the power p. So as you can see here, what's happening is you're going from a to the first to a to the p, which is p minus 1 steps. And in p minus 1 steps, if you get back to your original a, then a is a strong liar for the primality of p. Now you note that this can only happen if the number of steps it takes to get from A to A the first time is a divisor of p minus 1. So in this case, we're looking at A is 2, P is 17, and so we want to ask the question, is P prime? Well, the number 2 arrives back at itself at 8 steps here, and 8 is a proper divisor of 16, and therefore it goes around this loop twice, ends back at 2, and therefore it becomes a strong liar that 17 is a prime number. Now the thing to note here is the more divisors that n minus 1, or in this case p minus 1 has, the more likely you are to get a result that states that p is, where A is a strong liar for p, even if p is composite. So if we can somehow remove divisors from n minus 1 when we're randomly generating numbers, we can lower the probability that we have a prime that has a lot of strong liars, or a composite, an odd composite, excuse me, with a lot of strong liars. And at the bottom of this, I just showed a few of the results of running this website that I found interesting. So the Miller-Rabin implementation goes like this. First, we note that a to the p congruent to a mod p is equivalent to the congruence a to the p minus 1 equals 1 mod p by dividing both sides by a. We then subtract 1 from both sides to get a to the p minus 1 is congruent to 0 mod p. Now we note that the p minus 1 is even because p is an odd number that we are testing for primality. Because of that, we can factor the left side of the equation by completing the square. And in fact, we can continue doing this while p minus 1 over 2 to the n is odd, or is even, excuse me, until that number becomes odd. So we do that by finding an odd integer d and positive integer s such that p minus 1 is d to the 2s. And then we rewrite the congruence as you see here. Now, if any one of the terms in this congruence is 0, then the overall congruence holds true, and therefore A is a strong liar to the primality of P. This is some pseudocode. The takeaway here is just the ease of implementation of this algorithm. The most difficult step to implement is step 4, and that is just modular exponentiation by squaring. This is only 11 lines of code, which again illustrates the ease of implementation of getting Miller-Rabin correct. So my first question when I saw this is, how tight is this 25% guarantee? So I wrote some code that goes through and it just iterates through numbers and tests every single base A for any odd composite number and reports back how many of those numbers were strong liars. So this graph shows the results of that code for the first 2 million, for numbers less than 2 million. So this chart shows all odd composites less than 2 million and what percentage of those composites for each number were strong liars. Now, the thing to note here is the vast majority of numbers are clustered down here around the 1%, 2% range. The other thing to note is that this density is very much decreasing and compressing, so it keeps getting better and better with bigger numbers, which is great news because when we generate random prime numbers, we're usually generating them with thousands of bits, not just under 2,000 or 2 million, excuse me. The other thing to note is that there are these classes of prime numbers that asymptotically approach limits. So here's one that approaches 25%. There's another one here that approaches 16 2/3. I found that interesting, and on the next slide, we'll see that these classes down here at the bottom actually are very deterministic. So any prime that is written as the product of two primes, m and 2m minus 1, where both of those are prime, m can be computed using these equations on the right. So this is more just an interesting observation that I made. You wouldn't want to actually implement this because there are an infinite number of these classes of primes. These are just the ones that showed up for very small n. However, these observations at the top are more useful, and that is that each of the numbers that have a lot of strong liars have very few prime factors, and they that number -1 has a lot of small prime factors. So if we can somehow eliminate things that either have very few prime factors or that have a lot of very small prime factors for n-1, if we can eliminate those n's, then we can eliminate a lot of these cases where we get a lot of strong liars for a particular number. This is a cumulative distribution function, and again, the takeaway here, what this is showing is what percentage of numbers less than or equal to a specific number as a percentage, what percentage of numbers less than a particular number is less than this number on the x-axis of strong liars. So, for example, at 2 million, 99.5% of the odd composite numbers under 2 million have fewer than 0.4% bases that are strong liars. And the key here, again, is as these numbers get bigger, the number of strong liars decreases as a percentage. So this first number is for numbers less than 1,000, then less than 2,000, and it just keeps tightening up and tightening up and tightening up, meaning that fewer and fewer numbers have a lot of strong liars as n gets large, which again is great news because we're generating very large primes. So OpenSSL is the de facto open source implementation of the SSL TLS security suite. One of the things that it provides is a prime generation algorithm. And so let's dive into how that's actually implemented. So prime generation in OpenSSL follows the following algorithm. First, we generate an n-bit cryptographically secure number n where the first and last bits are 1. The first bit must be 1 because you need exactly the number of bits requested, and the last number has to be 1 because you want an odd number. The OpenSSL implementation also sets the second highest bit, but there is a to-do in the code that indicates that that is not intentional and will eventually be resolved. Next, we compute n mod p for each of the first 2048 prime numbers p up to 17,863. Basically, then we iterate through this loop and continue incrementing the random number that was generated by 2 until neither n nor n-1 is divisible by any of those first 2048 primes. If we increment n beyond the number of bits that were requested, so if we asked for 1024-bit prime number and we got something very close to that limit and incremented into 1025, then we just start the algorithm over. So once that loop completes, we have a number where n is not divisible by anything less than or equal to 17,863, and n-1 also has no such factors other than 2. So at this point, all we do is we run a number of Miller-Rabin Primality checks, and we choose the number of rounds based on the number of bits in the random number we are generating. And again, as you remember from before, as we generate bigger and bigger n, the probability that we have a lot of strong liars for a composite, an odd composite n, goes down. And because of that, the bigger the number, prime number we request, the fewer rounds of Miller-Rabin we have to run, which is, again, great news. So the algorithm runs these 3 rounds of Miller-Rabin, and if either n or n-1/2, if generating safe primes, are found to be composite, then it restarts the algorithm. Otherwise, it returns the n as a prime number. And the reason why it tests it on n-1/2 for safe primes is because some factorization algorithms have a complexity related to the problem of factoring n-1. That is why OpenSSL's random number generation attempts to ensure that both n and n-1 have no small prime factors. I will say finally that this reference at the very top of my bibliography for Keith Conrad's notes is a great reference. It has very good information if you'd like to delve into this topic further. That is my presentation, and thank you very much for your time.